I love graph theory, and let me explain to you why. Graph theory helps us formulate problems that are very real in this world. One example of a practical application is the 7 bridges of Königsberg problem. If you've ever heard of it. If not, don't worry about it. I'll tell you about something completely unrelated today. Today I want to talk about trees. So there's a thing called Cayley's Theorem, and Cayley's Theorem says that if there's n vertices in a tree, and I'll talk about what a tree is in a second, if there's n vertices in a tree, there's n to the power of n minus 2 distinct labeled trees on n vertices. Just keep that in mind. You can semi-forget about it. Let me tell you what a tree is first. There's a ton of equivalent definitions, logically, of what a tree is. A tree, well, one logically equivalent statement, a tree is a tree, obviously. Another one is, it is a connected graph with no cycles. A cycle is when you start and you move on edges and you appear back to the same point without going back and forth on the single edge. So, essentially, another piece of essential knowledge is there's no such thing as floating edges. So, all edges connect to vertices. That's another very fundamental thing in what I mean when I'm talking about graph theory, or when I'm talking about any of this stuff of what a tree is, etc. Another way to say what a tree is, tree is something that is connected and has n minus 1 edges. So n minus 1 edges means that if there's n vertices, there's one less edge than there are a number of points that those edges connect. That is also a tree. Another way to say what a tree is any 2 vertices of T have only one unique path connecting them. And a path means there's no going back and forth on the same edge. Remember that. Another way is T contains no cycle, but adding an edge will create exactly one cycle. And the last definition is each edge is a bridge. And a bridge means if you remove that edge, then you will have a disconnected graph. A connected graph means that there is a way to get from one point to the other for any 2 points, any 2 vertices. I call them points, but they're vertices. A bridge means that taking that away will no longer make that true. You will not be able to get from one part of the graph to the other. So, every single edge in a tree is a bridge. Okay. Well, a bridge is, whoops. My phone is overheating, so I'll put it in the shade. A bridge, or a tree, is a very relevant concept to real life. And I wanted to demonstrate using a native plant today, because I love native plants, Lemonadeberry. So let's take a branch of Lemonadeberry. I don't want to rip anything out, but let's say we have this little branch right here. Every single leaf, and it's literally called a leaf in math too, the endpoints here, the tips of the leaves, we'll call all of those vertices. And also, where they connect to the branch, that's also a vertex. So, vertex, 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 vertex. There's any branching out into 2 parts, like sort of like what we have here, that these would also have vertices. So all real life plants mathematically are trees. Besides really, really rare exceptions, usually due to human intervention, if there's like a branch branching out and coming back together again, 99.99999% of all plants are mathematical trees. So now that we have every single point of contact here with the leaf, that's a vertex, and every single thing connecting those points of contact are edges, and ends of leaves are all vertices, and those vertices are called leaves because they're the last one in the branching out. Okay, hopefully we're all on the same page. So, according to Cayley's theorem, let's label every single vertex, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm just gonna say there's 10 of these here. So first, and we ordered them, like they're literally labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We take the smallest number that is a leaf. Let's say that's this leaf right here. We take the smallest number that's a leaf. Well, first, this whole thing is a tree. That's 1. Then we take the smallest number, this one, remove it. The rest of that is also a tree. Okay, now let's take the second smallest number that's still a leaf. Let's say this one was labeled number 2. Then we remove these 2. The remaining part is still a tree. It's a branch and still branching out. Every single thing is critical. Keep on removing all of the leaves until you only have the branch. And then you can remove parts of the branch up until you're down to just one stick with connecting 2 vertices. And at that point, you can't remove anything anymore, because if you remove something, it's no longer a graph that's connected. So you're down to 2 points. So now you have the total number of vertices minus 2. And there is n trees for each one. So there's n to the power of n minus 2 distinct labeled trees on n vertices, because you can change the labeling every single time, the way you label the vertices. Isn't that cool?